Hi everyone, and it's a great pleasure to give a talk on this topic. So this is joint work with Harry Buhrman from QSoft, Laura Mančinska from Copenhagen, Noah Linden from Bristol, and Ashley Montanaro from Bristol and PhaseCraft. And we are also known as quantum majority, so this group of people. So let me start with some bold statements, and I want to start with a manifesto. So this is a conference on quantum computing, and it's not surprising. We all know that, quantum mechanics is described at the fundamental level, and therefore all information is quantum. To put it another way, we could say that there is no such thing as classical information, or if you want to be more precise, well, the classical information is just measure zero subset of the real thing, which is the quantum information. Okay, so, and also we should think algorithm, but the algorithm really is a CPTP map, so it maps quantum states to quantum states. Okay, and from this perspective, computer science is irrelevant because it just describes measure zero subset of all possible things that we could in principle do. And as people that study quantum computing, we should really focus on problems with quantum input and quantum output, instead of trying to, race and for some quantum speed ups to compete with this irrelevant zero subset of things we could do. So that's the mindset that we have. And okay, so if this is too radical, then maybe I will give you kind of a watered down version of the same motivation. But if you agree, you can also sign the manifesto that I just posted on Slack. All right, so here is the manifesto light. Okay, so it's as follows. So basically, imagine you are designing quantum algorithms, or you may be programming quantum computers, and you could say, well, quantum computer is just some device where you put in bit strings and some bit strings come out, and then there's some quantum magic that happens in the middle. Okay, but this is not very insightful or very accurate way of thinking about things, because a quantum algorithm really is a step. It's a process of many steps. So there are many such kind of boxes where quantum magic happens. And in between these boxes, what's being shuffled is quantum state. Okay? And so just from the very practical perspective of designing new quantum algorithms or programming quantum computers, what we want is as many as possible these boxes that have quantum input and quantum output. Okay? And in fact, we already have quite a few interesting primitives like this, like one Fourier transform, or one step of Grover iteration, or swap test, and so on. Okay? And so, what we really want is to have as many as possible these fully quantum primitives. Okay, so we're not stuck in this mindset of bit strings as input as output, but we want to have natural problems that process directly quantum information. All right. Which is a simple primitive that's used in probabilistic computation. And in general, probabilistic computation is always a good source of inspiration. So majority vote is simply you're given some bit string and you just want to find which value occurs the most often. Okay? And this is used in amplifying success probability of basically almost any probabilistic algorithm. It's also used in error correction to get rid of a couple errors that have occurred. And it's even used in some democracies. All right, so so what we want to do is we want to have a quantum version of this. So this is such a fundamental primitive, and it's somewhat surprising that there is no quantum version known up to this day. And so here is one proposal. So it could work as follows. So let's say you have some kind of device, some kind of box, and you can press a button and it spits out a state. Okay, and so this is it was very expensive to build this box, and it maybe takes some time to produce the state. So it's a very valuable state. And you want to kind of understand the state in some sense. So you would just press the box, this button several times, and you will get a bunch of copies of this state. But sometimes the device might fail for whatever reason, output some other state. Okay, and so for sake of simplicity, we're going to assume that this other state is orthogonal to the intended state. And in fact, we're going to assume that there is only the state space is just a single qubit space, and therefore there's a single unique orthogonal state up to global phase. Okay, and you can argue if this is reasonable or not, but just for the purpose of this this work, this is the model we're going to use. All right, so now if you press the button many times, you're going to get a string of these states, and the task is simply to determine which state occurs most often. Is it psi or is it psi perp? And what makes this problem non-trivial is that we don't know in what basis these states are. Okay, so if it was, so basically, and also, what I want to say is there's no point to compare with the classical case, because classically you can always compute majority of a given bit string, and so here really the difficulty is in the fact that we don't know what the basis is. Okay, so that makes the problem non-trivial. And to motivate it even more, and especially this kind of output model where we have these discrete set of possibilities, you can think of this as computation in an unknown basis. So namely, imagine that you have two parties, and maybe one party is somehow computationally limited, and it cannot perform the computation at once, so it sends the information to the other party that's much more powerful. But however, during this transmission, the information gets somehow messed up by, let's say, some unitary operation u. Okay, and what arrives is some state psi and psi perp at the other end. Okay, and well, okay, so let's say this powerful party was able to somehow compute the majority of these states even without knowing the basis. Then sending back the information would just restore the right basis, because let's say you can imagine these two parties, maybe they are so misaligned reference frames. So one has some XYZ axis and it's hurtling around in space, and it's not the same XYZ axis as the one that's sitting over here. Okay, so that's it's a very reasonable setup, and you can also imagine kind of like a crypto spin on this. You can imagine maybe actually this party applies the U on purpose. And then afterwards, when they get the answer, they apply the U dagger basically to get back in the right basis. Okay, so this is the kind of setup you can have in mind where this makes sense, and you can see that the majority vote, this quantum majority, is just a special case of computing an arbitrary Boolean function in this model. Okay, so now let me make the problem more precise. And so what we want to do, we want to compute a Boolean function in a unitary covariant way. So namely, let's say we have a function from n-bit string, and you can imagine the input could be just given as a standard basis state on n qubits, and the output will be just a single qubit state, either 0 or 1. But however, you want to compute it irrespective of what basis the input is given, and the output has to be in the same basis. Okay, so for any x and for any basis u, you want to implement somehow this transformation. Right, and so that the word covariant simply means that the basis of the output is varying in the same way as the basis of the input. Okay, so here's an example. So let's say you want to compute XOR on 2 bits. So here it would be just the XOR of 0 and 1 is 1. And we want to do this in any basis. So for any u, so we want to implement this kind of transformation, for example. In particular, if u is equal to x, we want to implement this transformation. Okay, so namely, we want to map 1, 0 to 0. Okay, but now we have a problem, because this is not compatible with the definition of XOR. This is not compatible with what we wanted to do. So then it seems like, ooh, we have a problem. But in fact, well, what we need to do is simply we need to change the definition. Okay, we need to change the statement of the problem. So basically, we have to restrict to functions that are themselves covariant, or you could call them also self-adjoint, meaning that if you negate the input, then the output also negates. Okay, and so this negation is just a special case of an arbitrary unitary that could happen, and the function has to have this property for the problem to make sense. All right. So now what we also going to do, so this is not necessary for the to make sense of the problem, but just this is a simplifying assumption. What we're going to do, we're going to restrict to functions that are symmetric, namely the value of the function depends only on the Hamming weight of the input. So let's look at an example. So let's say we have a function like this. We have on 3 bits. So we need to define it only for all possible Hamming weights, which is from 0 to 3. And for example, this particular function just corresponds to majority, because on both Hamming weights, it outputs 0, which is the majority of bits. And then for the high Hamming weights, it outputs 1. Okay? And you can see that the second half of the truth table is just kind of reflected and negated first half of the truth table. So you need to only specify the function on half of the inputs, basically. Okay, and another observation is that having n even is bad. So the problem doesn't make sense if the number of arguments is even. So for example, let's say you want to compute a function on 0, 1. So by this covariance, or by self-duality, if you negate the input, the output should also negate. And then by symmetry, you can just permute these bits back in the same order, and you see that the function on 0, 1 should be equal to the negation of the function of 0, 1. Okay, so it means that basically whenever the number of arguments is even, then if you look at strings that have half-half, or Hamming weight is half zeros, half ones, then you cannot really define the problem. So basically, we're just going to restrict to odd n because of this. All right, so let me now formally state the problem. So we are given some arbitrary Boolean function on n bits. We assume it's covariant or self-dual, symmetric, and n is odd. And we are given the input as a standard basis vector, but in an unknown basis. And we just want to produce some state, a single qubit state, which could potentially be mixed. And it should be as close as possible to u of f of x. Okay, so the value of the function in that same base. All right, so, and as a measure of success, we're going to use the worst case fidelity. So namely, for any function f, we can just assign a number, which is we maximize over all algorithms, namely all CPTP maps. And then we look at the worst case input. So basically, the input is determined by a bit string and a unitary. And so we look at the bit string in some arbitrary basis u. We apply the algorithm, and what should come out should have a big overlap with the desired state u f of x. Okay, and so basically what we want to do is we want to find for a given function f what is the best possible fidelity we can achieve, and we want to have a quantum algorithm that runs in polynomial time that achieves this fidelity. All right, and so this is basically what we're going to do in this talk. All right, so let me now state the results specifically on the majority function, and then later on we're going to look at the general case of arbitrary functions. Okay, and so as I said, we can't really, the problem doesn't have a meaningful classical analog, and so if we want to compare against something, we can compare against a trivial strategy. Namely, if we want to compute a majority of a bunch of states, it's just we have basically a tensor product state. The simplest thing we could do is just output any qubit at random. Okay, so if most qubits are psi, then this will, with good fidelity, gonna give an output that's psi, basically. Okay, and so we want to know, can we do better than this trivial strategy, basically? Okay, and we're going to look at two cases. So one, when there is no promise, namely the input string can have arbitrary Hamming weight. So in particular, since n is odd, the Hamming weight could be very close to being half. So it could be either slightly more than half or slightly less than half. And the other case is when we have a promise, namely we are promised that either the Hamming weight is really large or the Hamming weight is very small. So somehow we are excluding a region around this middle point. Okay, and so somehow, if it's half-half, then it's hard to determine, at least for this trivial strategy, it's hard to determine the majority. Okay, so you can quite easily see that for the trivial strategy, the success probability or the fidelity basically is going to be, for the no promise case, is going to be 1/2 plus the size of this small gap here, which is 1/2 to the 1/2n. And so, it's very close to half, but that's what it is. And in this case, basically, if you are in this region here, at least 5/6 of the states are the right ones. So with fidelity 5/6, you will output the right state. Okay, and so we want to know, can we do better? And of course, the trivial strategy, it doesn't make the states interact in any way. It just outputs one of them. And what we want to do is somehow smash them together and see if we can do better. And indeed, we can. And so what happens here is we show that in case of no promise, the optimal fidelity will look like this. So of course, it's still going to be close to half, but it's not going to be as close as in case of the trivial strategy. And somewhat surprisingly, when you have the promise that that you have basically that the Hamming weight is at least it's large enough, then you can actually get arbitrarily close to fidelity 1. So basically, if the number of states goes to infinity, then you can actually achieve this task basically as good as you want. All right, so these are our results on a majority function. And so now let me say a little bit about how we prove these results, and also what happens for general functions. Okay, so what we're going to need is some representation theory, but let me just try to simplify it as much as possible. So let's just look at two systems, two qubits, and let's look at the symmetric and antisymmetric subspace. So let's say we have a state that's 0, 0, so this state is symmetric. We apply an arbitrary 2x2 matrix A, B, C, D. Okay, so you can easily compute what you get is just going to be this state here, and you can write it as a linear combination of states that have Hamming weight 0, that have Hamming weight 1, so these two entries here, and then the state has Hamming weight 2 here. Okay, and so you can see that this guy, it lives in a symmetric subspace, and in fact, any state lives in symmetric subspace can be described like this by some values A and C. Okay, so what's left over is one more dimension, and that's the antisymmetric subspace, and it's just this dimension is spanned by the singlet state. And the singlet state has the magic property that for any 2x2 matrix ABCD, it could be even symbolic matrix, whatever, it's going to be always an eigenvector with eigenvalue, the determinant of that matrix. Okay, and so we can see that basically in the symmetric and antisymmetric subspace, an arbitrary matrix ABCD somehow decomposes in some nice way. Okay, so let's do the following. Let's just take this antisymmetric state, the singlet state, and put it as the first row of some matrix U sure. So this is going to be called sure transform. And the other three vectors of Hamming weight 0, 1, and 2, let's just put them as the other three rows of this matrix. And so this is going to be unitary matrix because these states are just orthogonal by definition. And well, this has the nice property that if you take arbitrary matrix ABCD, and if you conjugate it, so if you just change the basis, it's going to block diagonalize like this. Okay, and so this top block here, this 1x1 block, it just corresponds to basically this eigenvalue of the singlet. So you get this determinant of this ABCD matrix. And then this 3x3 block corresponds to symmetric subspace. And you see you get some nice matrix over here. Okay. All right. And similarly, also, if you take the swap operation, you can see that the swap operation, it just has eigenvalue -1 in this antisymmetric subspace and eigenvalue +1 in the symmetric subspace. So also not only these tensor power matrices decompose nicely, but also permutations decompose nicely. Okay, and another important fact is that these blocks over here, in fact, they are homomorphisms. So basically the map from an arbitrary matrix ABCD to this one, to the determinant, or this 3x3 matrix is actually homomorphism. It has this property. So for the determinant, it's obvious, we already know, but for the 3x3, it's not so obvious. Okay. All right, so there is a generalization of this on n qubits, and what it does, it just maps n qubits space into a direct sum of space that consists of two registers, and these registers have some dimension m lambda and d lambda, and basically if you apply this to an arbitrary tensor power matrix, then you're going to get something in the first block, and so this would be one of these funny homomorphisms, and if you apply it on an arbitrary permutation pi, you're going to get something only in the other block. Okay, so I will call this the unitary register and the permutation register. And an important fact from the algorithmic perspective is that this can be implemented in polynomial time, namely n to the 4 times log n gates. And this was there's a really nice paper and also an algorithm that you can actually run by Kirby and Strauch. But this has been studied earlier. We already knew for a long time this was polynomial. But we know also now that it's n to the 4th. Okay, so let me describe at a high level how our algorithm works, and unfortunately, this will make sense only for those who already know some representation theory. But so let me just give you kind of the high level idea. So basically, so we are given this state over here, and the first thing we do is apply this short transform on n qubits, and then we measure this lambda. So we basically measure in which block we are. And this is also known as weak short sampling. So this is something Andrew mentioned. So this is used in, for example, a hidden subgroup problem and so on. All right, and then we discard this permutation register. So remember, we had these two registers. One was for the unitaries, another for permutations, and we simply discard the permutation one. And then we are left with something on the unitary register, and we just need to apply some unitary covariant channel that has a 1 qubit output. So this is kind of a high-level structure of the algorithm. So let me just comment briefly on these steps. So basically what's important about these steps 1, 2, 3 is that they are reversible. Namely, we can do them without loss of generality. We don't lose any information. And this has to do with the fact that you can basically, because the function, we assume the function to be symmetric, so we can symmetrize the input state. And therefore, on a permutation register, we will just have maximally mixed state, so we can just throw it away. And the state has block structure, therefore measuring the lambda does not disturb it. Okay, so yeah, so then in what we are going to be left with in step 4 is some state of some random dimension, and then yes, and then only the final step will depend on the function f itself. Okay, so basically, so these first 3 steps are kind of generic, and only the last step will depend on a function that we actually want to compute. All right, so what is this last step where we apply some arbitrary covariant channels? So we need to kind of understand what these channels are. And what you can show is that for any lambda, there are only, so this family of channels has only one parameter, basically. So there are only two possible channels you could do. And one sort of intuitively corresponds to partial trace, and the other one corresponds to the so-called universal knot, meaning that any state is mapped to, as close as possible to the orthogonal state. And to parameterize an arbitrary unitary covariant channel, we just need one number, a probability, which says, are we going to do this map or are we going to do that map? And in general, we do some kind of convex combination of these two maps. And they simply correspond to, in representation theory, to removing corners from this diagram. And so this has to do with what's called a Clebsch-Gordon transform or its dual form. And sort of to analyze this, you need to understand symmetric subspace on L and L+1 qubits. And we showed that these maps can be implemented with a small number of gates. Okay, so now let me state this our result more formally. For any Boolean function that is symmetric and covariant, what we show is that these parameters in this covariant channel in the final step, they can be optimized using a linear program that is of fairly modest size, just of size n/2. And this program, what it does, it spits you out the fidelity of the best algorithm, what fidelity it can achieve, and it spits out also these parameters that you should use in this generic algorithm. Okay. And also we can implement any of these algorithms for computing these functions with n⁴ log n gates. And basically, the most complicated part is just the Schur transform, and then implementing these covariant channels is relatively straightforward. So yeah, so here is just an example of how this looks like if you compute this fidelity for, let's say, all 7-argument Boolean functions. So remember, the truth table is just the function depends on Hamming weight, and because it's covariant, the second half of the truth table is just inverted and reflected first half. And so, these numbers at the bottom are the fidelities for different functions. And in fact, you can see these fidelities actually, if you want to determine them, you should sort of read this thing backwards. So this is 0, 0, 1. So if you go 0, 0, 1, so for this function, the fidelity is this value over here. And you can see by the structure of this tree, in fact, the fidelity depends only on the gap around the center. So how, for how long is the function constant? And then at some point it flips, and that point determines the fidelity, and what happens afterwards doesn't matter. And this is also a phenomenon that happens in quantum query complexity for symmetric functions, that the query complexity depends only on the gap around the middle. Okay, so now let me state a couple of open problems. So, so you might question the model that we are using, and indeed, I think it's meaningful for the algorithm, like for this box that spits out these states, to fail basically in continuous ways. So it doesn't have to be psi versus psi perp. It could just be some kind of distribution that's maybe it's peaks at psi, but it could be some distribution on block sphere. I think that's a very nice question. Also, to extend this to qubits, so dimensions bigger than 2 or more than 1 output. Also, you could throw away this symmetric restriction. It can be any function, doesn't have to be symmetric. It doesn't have to be a total function, it can be partial. I think it would be really nice to understand the connections with query complexity model sort of in a more standard sense. So we have this model where we just have some state and we just have one copy of the state, but I think there seems to be some parallels with query complexity that we could understand. And finally, I'm really grateful to the program committee that they accepted our talk, even though our result has no applications as far as we know. But I think it would be nice to have applications, and maybe also in a crypto, some maybe cryptographic applications. All right, so that's all I want to say. Thank you.
Thank you, Marius, for a great and entertaining talk. So I encourage people to ask questions on Slack. Most of the questions were answered, but there are some. Okay, let me just maybe ask one question from my side. So, having met your manifesto, okay, you focus on the worst case fidelity And I understand that because of this unitary invariance, you could go to covariant channels, etc. I mean, it would be like that if you focus on average case fidelity, and right, and then in the light of your manifesto, here you focus on this universal but maybe then you can abandon this condition that n is odd. You know, can you comment on this?
Yeah, so I guess the reason we focus on the worst case is because that's sort of what you typically do in computer science, if you're very kind of paranoid. But yeah, we could focus also on average case. But the reason for this, the n to have to be odd, is simply because we're looking at total functions. So we could just say we're looking at partial functions, and then we could allow n to be odd, and then we could say, well, we just restrict the input to bit strings that don't have the Hamming weight exactly half-half when it's not defined. So like, yeah, we could get around that by other ways.
Thanks. Okay, let me try to pick some questions. There are quite a few popping out. What about mixed error noise in the? Sorry, this one was answered already. Right. Okay, one more question from me. Sorry. So you focus on those symmetric functions, and you implemented show transform in your protocol. But you said that you have symmetry, permutation symmetry. So could it be like the show transforms qubit registers into ERABs of symmetric and a unitary group? Like maybe some simpler, like can't you just use like a transform just for the unitary group? And that would maybe simplify gate counts and stuff like that.
Right. Yeah. So that's interesting. Yes, because the only thing we do is we do this weak Shor sampling, and then afterwards we have to do this kind of covariant channel. And you know, in principle, there is also something called generalized phase estimation that does the weak Shor sampling in a different way using the symmetric group. And yeah, I think one could imagine in principle that, and especially also we throw away this other register, this permutation register. So I think it's not inconceivable that one could do this more efficiently. Yeah, no, I think that's an interesting point. Yeah.
Yes. So, question from Thomas Widig. Can you give a hint for some potential crypto applications?
Well, this is this idea of computing in an unknown basis, where you basically, you can imagine that you on purpose apply an unknown unitary to all of your input qubits, and then you send them over to somebody, and they perform the computation without knowing what basis it is. So you can imagine, like, for example, for counting the votes, you don't want to know, you know, are the Republicans or Democrats winning? You just permute the labels, basically. You can permute them discretely, but you could also permute them continuously. And then if the other person is still able to compute a function, like determine the majority, then they send you back the answer, and then you can, you know, undo the unitary. So you can basically do this, you apply and then, you know, undo the unitary on purpose. So that's kind of the crypto setting that I have in mind.
Thanks. I guess we have to move the rest of the discussion to the roundtable. Maris will be present there after the next talk. Thanks again, Maris. Right, and now we move to the next speaker.